Hello everybody, this is Tyler, covering 14.3. Today I'm gonna choose number 19. It asks, part A of it asks to check the linearity of this function, three-dimensional function fxy equals e to the negative x times sine y near 1 and 2. And this part isn't actually asking me to get fxy, so partial z over partial x and partial z over partial y, but rather they ask me to actually plug in those individual values 0.9, 1.0, 0.1, 1.9, 2.0, 2.1, and they want to compare that table with the other table which has two decimal place precision 1 point, so it would be like x equals 0.99, 1.00, 1.01, y it's gonna be 1.99, 2.00, and 2.01. So I'm gonna import the table that I wrote previously. Okay, so these are my table values that I put in calculator, and the book actually asked me to record on up to 4 decimal places, and those are the results. And the point is to compare these two tables, and obviously the left one varies more, so like deviation is a lot larger than the second one. So the left one is first and the right one is second. I refer to them, and I actually try to calculate the differences between the data. So on the first table I got 0.015 between 1.9 and 2.0, given that x remains constant. And next time I got 0.0187, which differ in third decimal places. And same thing happened when x was 1.0 and constant. It varied in third decimal places by like 0.003, and the same exact thing happened at x equals 1.1. Instead, on the second one on the right table, I almost got the constant changes or deviation between certain changes over x or y. So given that I got 0.99x as an x, for any change that occurred, by any change I mean a change of y by 0.01, I always got the differences of 0.0015 here, and I got 0.0014, which differ in the fourth decimal places, but which is really subtle by 0.0001, and compared to the left one, it's like 30 times less variation, and I don't, to be honest, I don't see any differences between those differences. So it's a little complex differences, but that's what slope means. So this one is almost, I can say this one is almost linear over over y difference, given that x remains equal. And same thing happened when I set y constant. You can see the changes were 0.033, same exact changes no matter what y value we set. And that only proves that this one is almost linear, except for a few variances like this. So therefore I can conclude that second one, or the right table, is more linear than the first one. By linear I mean looks more of line than a exponential function that changes the slope, that the change of differences or slope changes over time. So I'm gonna use the second one to get the part B, asking me to actually get the local linearization of this function, and compare it with the conventional method, fx(xy) and fy(xy), using those two values. Okay, so I just wrote down the conventional way of doing it. I was just learning classroom that by calculating fx(xy) and fy(xy), we can get this approximate value of our plane, and in this case fx was negative e to the negative x sine y, which gave me negative 0.335, and fy(xy) was e to the x cosine y, which was negative 0.153. So plugging in those values, sorry about mistakes, I got fx(xy) times x minus 1, because it's near 1, x equals 1, y equals 2. I want to use value x minus 1 and y minus 2, and the second term would be negative 0.153, exact same value we got, and times y minus 2. And those values will differ greatly, more and more, as x and y gets apart from 1 and 2, but as long as x and y, the value we're trying to approximate, is near 1 and 2, we're gonna get almost exact answer, almost no error, just like we did in Taylor polynomial. And now I'm gonna use the table. The second table gives the value of 0.0033 over change of 0.01x. So delta x was 0.01. Therefore, delta z over delta x would be 0.0033 over 0.01, which equals to 0.33. Let's compare those two values, 0.33 and 0.335. It's almost same. Oh, never mind. This is negative value. I'm so sorry. Negative. And we're less accurate in the way that we approximated approximately, but this is really a prominent way of doing it. And now I want to get dz over delta z over delta y, which we got as negative 0.0015 over negative 0.01 delta y. This was constant at the raw 2.00 and 1.00. Left, right, up, down, all the differences were constant as long as we are given x or y, either x or y are constant. So this gave me negative 0.05, which almost matches with negative 0.153, and so as a conclusion never mind, I didn't write the approximation form. So f, in this case, I'm gonna use the slope of z to x, if that's the right expression, negative 33 x minus 1, negative 1.15 y minus 2, plus at the 0.3345 right here at the value 1.00 and 2.00. Therefore, I can conclude that the equation I got is almost equivalent to the approximation we used by partially differentiating x and y over to to the respect of z, or vice versa. I'm not sure. Yeah, thanks for watching, and it was a pretty long video, but I try to embed a lot of tables and data, but it looks like it's actually faster by writing them down than copy and pasting. Alright, thank you.